Let's recall the definition of the equivalence relation. So if we have a set S, then a relation R on the set S is a set of ordered pairs of elements of S. That is, a relation R on a set S is just a subset of the Cartesian product S cross S. Now, a relation is an equivalence relation if it is reflexive, symmetric, and transitive. A relation is reflexive means that the pair A comma A belongs to the relation for any A in S. That is, for any A in S, A is related to S. The symmetric property means that whenever the pair AB belongs to the relation, so does the pair BA. In other words, A tilde B implies that B tilde A for all AB in S. And the transitive property means that whenever the pair AB and the pair BC belong to the relation, so does the pair AC. In other words, if A tilde B and B tilde C, then A tilde C for all ABC in S. Okay, so I'm now ready to define equivalence classes. So let's say tilde is an equivalence relation on the set S. Again, it means it's a set of it's a set of ordered pairs of elements of S, where that set satisfies the reflexive, transitive, and the symmetric property. So given an equivalence relation tilde on the set S, we define the following set. This is the set of all x in S such that x is related to A, where A is fixed. And this is denoted by the symbol here, where we write A within square brackets. So this is called the class of S containing A with respect to the relation tilde. So the class containing A of S is the set of all elements of S that are related to A. S slash tilde denotes the collection of all classes of S defined by the relation tilde. We say this set of all classes is called a vector set of the relation tilde. So this is called the vector set as well. So the vector set of S with respect to tilde is the set of all equivalence classes with respect to the relation tilde. Here is an example. Let's take S to be the set of all polynomials. For polynomials f and g, define f tilde g if the derivative of f is the same as the derivative of g. We saw before that this relation is an equivalence relation, and the question is, what is the class containing the fixed polynomial f? Well, if g belongs to the class containing f, that means that f is related to g, which would then mean that the derivative of f is the same as the derivative of g. And so remember that if the derivatives of two functions are equal, then they differ by a constant. So g of x must be f of x plus a constant c. So as a result, the class containing the polynomial f is the set of all polynomials of the form g of x is equal to f of x plus c. So in other words, the class containing f is the set of all polynomials that differ from f by just a constant. Okay, so if I ask you what is the class containing the polynomial x squared, Well, the class containing the polynomial x squared would be the set of all polynomials of the form x squared plus c. Here is an exercise. Okay, now here we define a partition. A partition of a set S is a collection of non-empty disjoint subsets of S whose union is S. So it's a collection of non-empty disjoint subsets of S whose union is equal to S. So for example, if I take S to be the set 1, 2, 3, 4, and if I take P to be the collection of subsets of S, so 1, 2, the subset 1, 2, the subset 3, and the subset 4. So these three are subsets of S, and notice that these three subsets are disjoint. If I take the union of these subsets, I get the entire set S. So then P is a partition of S. When I say that I'm taking the union of these three sets, I mean I am putting all the elements of these subsets into one set. Okay, if I take S to be the set of all real numbers, then if I take P to be the collection of subsets of R, where the subsets are where there are two subsets, one is the set of rational numbers and the other one is the set of irrational numbers. So I is the set of irrational numbers, Q is the set of rational numbers. Then this collection of subsets of R is a partition of R, because these two subsets of R are disjoint, and their union is the entire set of real numbers. Here I'm taking the set of all points in the plane R2. Remember, R2 means R cross R. So this is the set of all points in the plane, and here is the collection of subsets of R. So again, R2 is the collection of all ordered pairs of elements of R. Here is a subset of R, R2, S1, where I take all ordered pairs AB in R2, where A and B are non-negative. S2 is the set of all. So notice that S1 is basically the first quadrant of the plane, including the x and including the positive x-axis and the positive y-axis. S2 is the set of all ordered pairs AB in R2, where A is negative but B is non-negative. So this is the set of all. This is the set of all points in the second quadrant, including the negative x-axis. S3 is the set of all ordered pairs AB, where A is negative, B is negative. So this is the set of all points in the third quadrant, the negative or negative y-axis is not, negative x or negative y-axis is not included here. And S4, there is a typo here, this would be S4, is the set of all ordered pairs AB in R2, where A is non-negative, B is negative. This is the fourth quadrant, basically, with negative y-axis included. So S1, S2, S3, S4, this collection P forms a partition of R2. Proposition: any partition P of a set S determines a unique equivalence relation tilde on S such that P is the factor set of tilde. That is, P is the set of all equivalence classes of S. Again, any partition, given a partition P of the set S, we have this unique relation tilde on S such that the partition is equal to the factor set of tilde. The proof goes like this: for any AB in S, so we are assuming that P is a partition of S, that is, P is a collection of disjoint, non-empty disjoint subsets of S whose union is S. So for given AB in S, we define A tilde B if A and B belongs to the same subset in P. Then one can easily show that this is an equivalence relation on S, and that the equivalence classes are exactly the subsets in P. And it's pretty easy to see why that's the case. So for example, if I look at the equivalence class of an element A, what is that? Well, what is related to A? So what's related to A? Well, any an element is related to A if it belongs to the same set as A. So if A belongs to a subset of P, then and B is related to A, then B also belongs to the same subset. So you can, if you think about it, then you see that the class containing A should be the subset in P that contains A. Okay, so I'm not going to say any more words on this proof. So let's look at the next exercise, which I'm gonna go over a bit. So let's let tilde be an equivalence relation on the set on a set S. Then A belongs to the class containing A. Well, this is clear because remember, if tilde is an equivalence relation, then tilde is reflexive, which means that A is always related to A. So therefore A must belong to the class containing A. The number 2 says that A tilde B if and only if the class containing A is the same as the class containing B. Okay, why is that true? Well, it's an if and only if statement, so I have to prove 2 implications. Let's assume that the class containing A is the same as the class containing B. Well, then A belongs to the class, because A belongs to the class containing A, then A belongs to the class containing B. But that means that A is related to B. So assuming this, we proved this. Now let's assume that A tilde B. Now we want to show that these 2 classes are the same. So assume A tilde B. To show that these 2 classes are the same, we pick X in this class. So if X is in this class, then X must be related to A. But A is related to B, so by the transitive property, then X would be related to B, then X would belong here. So we showed that if X is here, then X is here. So then this class containing A would be a subset of the class containing B. Similarly, we can show that whenever X is in the class containing B, it must also be in the class containing A. So we can then show we have then showed that the class containing A and the class containing B are the same. The third one here says that given AB in S, either the class of A and the class of B are disjoint or they are the same class. That is, 2 classes are either the same or they are completely disjoint. How do I prove something like this? Well, again, if the intersection of the 2 classes is empty, then I have nothing to prove. But if it is not empty, then let's say X belongs to the intersection here. Well, then X is related to A and B both. So then X is related to both A and B. Well, if X is related to both A and B, because it's an equivalence relation, I can say that B is related to X and X is related to A. So then by the transitive property, B would be related to A. As a result, by 2, we know that the class of A and class of B are the same. So if there is something in the intersection, then the classes are exactly the same. And number 4 says as the factor set the factor set of classes forms a partition of S. Well, number 4 basically follows from 1, 2, and 3, because by 1, 2, and 3 we know that the classes are the distinct classes are disjoint, and their union is S, because every element of S belongs to some class. And by 1, every element of S belongs to some class, and then the distinct classes are disjoint. So as the set of classes forms a partition of S. Okay, so this is it. This is the end of my discussion on equivalence relations.